continue on the Bayesian estimation. Now, we have seen so far that making Bayesian estimation is, in a non-Gaussian setting gets a nonlinear estimation. Now, we made the simple assumption, if you like, where the measurement, the data, okay, are mixing by Gaussian and non-Gaussian. If you make mixing Gaussian and non-Gaussian random constant, random variables, the estimator becomes linear. On the other hand, we saw that if we look at the Gaussian and Gaussian, so in other words, I have parameters that are Gaussian and the observation that are Gaussian, then in this case, this estimator is linear. So for this reason, most of the usage of Bayesian estimation is for linear setting or linear estimator, which means that most of the case you try to recover the usage of a linear estimator because it's more easy. Okay, so you have a matrix time. No matter how complicated is the linear, okay, the estimator. So you might have a big matrix, a small one. It doesn't matter. It's linear. Okay. So perhaps you don't appreciate much the linearity of the estimator, but as soon as you enter into the messy non-linear estimator, then you appreciate the good. So that means that you need to see the bad to appreciate the good. Okay. Now the other story is that if we have a Gaussian setting, in Gaussian setting, the mean and MMSE coincide because the distribution is unimodal, and so when the a posteriori distribution is unimodal, you have the mean and the maximum that coincide. That's another nice property, because you need to say that you are doing a Bayesian estimation. You don't need to say is it MMSE or map. Now, in addition to that, computing the MMSE is usually much easier than computing the map. Because computing the MMSE, you need to compute the mean of something. Okay? Computing the mean means computing the moment. Computing the maximum of something is complex. It's usually complex, and you need to use some very specialized method to find the maximum. It's dropping everything today. So it's to find the maximum. Okay. So now let me stay on this line. So let's assume that everything is Gaussian. Okay. So we are in the Gaussian setting. Now, what does mean Gaussian setting? It means that the observation, the data and theta are both jointly Gaussian. Remember, x is the data, theta is the parameters. Okay? So if these two are jointly Gaussian, then that means that I can calculate, knowing the a priori probability density function, the a posteriori. In other words, my goal is the following. If I know that x and theta are jointly Gaussian, then that means that I know that those behave with a certain mean. So I have the mean of x, I have the mean of theta, okay? And then, the Gaussian is characterized by the second moment. And the second moment is the covariance. So the joint covariance for x and theta is the covariance matrix, which is a block structure. So block structure means that it's a partition in blocks. Now let's look at a little bit with this matrix. So assume that my measurement is a vector with n and the number of parameters which is p. Okay, no matter that they're Gaussian distributed with a priori, but the set of parameters to get to estimate set of knowns is still that one. It's still p. So that means that my mean. So the mean is characterized by a vector which is n entries, and then I have a vector of parameter which is p. Okay, so this one is n plus p times 1, and similarly the mean. What about the covariance? Now the covariance is block partition. Now the fact that it's block partition means that this CXX is the covariance on XX, okay, and this one is n times n, and that is the covariance on data for observation. Now then I have the second entry. This one is the covariance of theta. Okay, and now this is the covariance on a priori parameter. Now what is this? Oh, by the way, sorry, this one is p times p. Okay, so then there is another two matrices. Now these two matrices account for the covariance between x and theta, or theta and x, depending on which block of diagonal I'm considering. And this one is n times p or p times n, depending if it is the upper and or the low. So given that this is the structure of this joint probability density function, joint Gaussian. Now let's assume that the p theta, the a priori, is Gaussian. Now if this one is Gaussian, that means that the theta, the a priori, is normal with a certain mean and a certain covariance. Okay. Now, how do I get the a posteriori? Now, to get the a posteriori, what I need to compute is the following. So I need to use the bias formula. So what is the bias formula? Now, in this case, it's in the book somewhere. I don't remember which page, but in the book, you can find the computation when I know, that's in the book, when I know p, x, y, so when I know the joint probability density function, and I know, for instance, the p of one of the variable, okay? So I can calculate the conditional probability density function. So, and then I can calculate what we in this context call the a posteriori probability density function. So that means that if I want to get py given x, okay, that's in the book. Okay, that's in the book. So if I want to get the py given x, okay, now this is equal to p x y, okay, divided by px. So that means that I need to take, if I want to get this, okay, which is the a posteriori in our case, I need to take the joint probability and then compute this ratio. Okay. Now in this case that means that I know px. So if a px, which means that it's Gaussian, that is a jointly Gaussian, then I can compute this one as a conditioned Gaussian because it's conditional on x. Now on the other hand, if you remember, it's not surprising that when I mix this way, comes out a Gaussian distribution, because if I make a jointly Gaussian, if I calculate the conditional one, that means cutting. So when I cut the bell, I get a piece of bell. So when I cut a multidimensional Gaussian, cutting on a plane, I get the Gaussian. Now, in our case, that means that I need to take p x theta, and I need to divide by p x, okay, to get p theta given x. Now, you put the Gaussian here, you put the Gaussian here, blah, blah, blah. you combine, blah, 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 and then you get the result. The result is the one that is written there. So, in other words, in order to get this conditional PDF, for detail, see previous chapters. Now in book it's the full derivation is in, let me see if I can find it right away. So that's 3.5. 3.5. Section 3.5. Okay. So now, then what we notice is that the condition PDF, which means the a posteriori, is Gaussian. And this Gaussian, then, it's Gaussian represented by a certain mean and a certain covariance. Now, this mean is the mean of the a posteriori distribution. And this covariance is the covariance for the a posteriori distribution. Now, so since, in a Gaussian setting, the mean and the maximum coincide, and since the mean is the MMSE estimate, then that is the mean, and so this one is the mean of theta given x. But this one is the MMSE. Then since the distribution is represented by a Gaussian distribution, so for the Gaussian distribution, the mean and the maximum value coincide. And so for this reason, for the MMSE coincide with the map. So we found the MMSE. That's a good news. So we found the MMSE in a general way. So now, reading the MMSE, which coincide in this case, is the mean of the a priori plus a linear transformation with respect to the data. So the estimator is linear. Okay? So the estimator is linear. Now, an additional remark. What is the covariance? Now the covariance, this is the covariance. So the covariance here is the covariance for the MMSE, which is coincide with the covariance of the maximum posteriori. Now, what is that? It is C theta theta minus something. So what does it mean? It means that, if this something does not exist, it is C theta theta. But I have C theta theta minus something. So look at here as a variance. So this is the variance of theta, which is the a priori, minus something. So, the probability density function of the a posteriori is the probability density function a priori minus something on the variance, which means, our distribution is shrinking. And if it is shrinking, it's getting better. So that means that, it's more accurate. It is more accurate with respect to what? It's more accurate with respect to the a priori information. So, by observing, you gain. If you don't gain, it's not important to observe. Now, let's see this intuitive setting. If I observe, I collect x, I gain. Now, how do I gain? I gain because looking at here, now if this guy here, this one, which is, look, this one is the same as that. So now, if I observe something and theta and x are correlated, they are linked together, this term is different from zero. The covariance reduces And you know, and the estimator is estimating something, whatever it is. Okay, the reasoning. So what I expect the following. If before opening the door, my position is a big Gaussian, let me say, elongated along the table, okay, this is what the model says. The model says you need to describe the distribution as Gaussian. So what you do, you say, okay, I do the way, you know, where is the board? The floor, the wall is here, the table is here, that's a table. So what is the professor here? Well, you know, since I need to use a Gaussian model, so the a priori distribution of the position of the professor here is a Gaussian. That's what they say. Okay? Now, this distribution is p theta, which means a priori. Now, you know, when you open the door, what you can find is that the distribution after making the measurement is Gaussian as well. But you know, the covariance is smaller. Now, where the covariance is positioned, so where is this point of the mean of the a priori, okay, is not necessarily the same that remains a posteriori. So the covariance after, you know, perhaps is a posteriori is this way. This is the distribution of t theta given x, which means this is the distribution of the covariance after making the measurement. So after opening the door, after sensing where I am, my position, and so on. Okay. Remember, you know, the mean should not coincide. By the way, you see here, the mean of a priori is mu theta, and the mean of a posteriori is mu theta plus something. Okay. So this plus something is taking the mean and moving it. Okay. So this is the position of mu theta, and this is the position of mu theta plus c theta x, cxx to the minus 1, that is x minus minus, okay, which goes there. That is the maximum posteriori estimate, that is a minimum mean square estimate of the position where I am. No. So, and you know, look at the ellipses. It's a shrink, it's a smaller, should be smaller. Okay? So, you know, looking very, very much care, we will see that it's a smaller, but it is not necessarily oriented as the previous one. Okay? So, it's a smaller. In other words, if I calculated the determinant of that, the determinant of this one, which is the posteriori, is much smaller, actually much, is smaller than the determinant of the a priori. So you see how much I read from this stupid formula, okay? So you know, this is the comment on this one, that's the comment of this. That's it, and there is nothing else, you know? So this is the estimator. Huh? Now, so now let's customize. Okay. So let's assume that, for instance, our model is additive with additive Gaussian. So you know we have a data. Okay. Now this one is Gaussian, and that is always written here. And W is Gaussian. The noise is Gaussian. So, because of this setting, x and theta are jointly Gaussian. Now, my goal is to calculate, so since this model fits into the previous one, so my goal is to estimate, to get the estimator, okay? So I need to compute, you see here, you know, you see there. So what I need to compute is the mean of x, okay? You know, the mean of x here, if noise is zero mean, so the mean of x is the mean of these s theta, that depends on theta. So the expectation here is computed with respect to theta. Look at the, you know, what is written here. Since I need to compute the mean, I need to calculate the mean on x. The mean is calculated with respect to theta and w, because theta and w are the two random variables. Now, since the noise is zero mean, here the expectation goes to w, because, you know, in principle I should write plus the expectation of w with respect to w. Okay? But you know, this one is zero because of the assumption. Now, second, what do I need? You know, it's like I mean, picking up all I need to put into the code is like, you know, the lab, the workshop that you did. Okay, so what do I need to write the estimator so that I listen to music nicely? Okay, I need this. Okay, then compute it. So you first compute analytically on one side, then you see what, I mean, the minimal formula that you need to compute, which is this one. Then you calculate that, you fit into the code, and you know, that's first. Okay, then you need to calculate the CXX. So, you know, CXX is computed by the definition. So it's the expectation of, with respect to theta and w of what? By, you know, it's a definition. So it's x minus the mean times x minus the mean transpose. Okay, so that's by the definition. You know? So then, I mean, when I compute that, so I have the expectation theta. Now the expectation theta is acting just for S theta, and the expectation W acts only on W, which is the covariance of W. So, you know, that's, I mean, this is what is the CXX, okay? So the covariance of the data. And now, I mean, looking at there, so, you know, I mean, what I'm doing is this. So simply that, let me copy. So we have in front of us, because, I mean, yeah, let me copy, it's better to have it in front. Yeah. Okay. So now, as I said, we need the mean here, okay, which is there, and the mean is the one that, you know, goes here in our formula. Okay, that's the mean. Then we need the CXX. CXX goes here and there. Okay. Now, if I purely look at the estimator, I don't care about, you know, what is the covariance. Then, you know, goes just here. Okay. But I mean, deriving the estimator without having the perfect knowledge of what is the accuracy is like making half of the job. Okay. So, you know, it's like using the MATLAB codes that you can find online, and you don't care about what is the accuracy of the method that you're using. So, you know, that means that the first line is solving the problem. The second line is bounding your responsibility with respect to the commitment, with respect to the project manager that is coordinating perhaps a bigger project. Now, so this is CXX. Now, the third part, okay, which is C theta x. C theta x goes here, and you know, CX theta, which is the transpose of C theta x, goes here. Okay? So, and how to compute? Still the definition. So it's that one is the covariance of theta and x. So the covariance of theta and x means that I need to calculate theta minus the mean and x minus the mean transpose. Okay? Now, I do exactly as before, so I arrange all the terms in such a way that I isolate, you know, the dependency of the different part. So when I take x and I plug in the model, okay, that's what remains. And then, you know, that's it. I mean, this is what I need to compute. Now, everything depends on the model. So I did not specify right now how is S theta. Now you can imagine that the same estimator simplifies when S theta is linear. So let's see, this is a special setting. So if, let me paste, I want to paste the same here. Yeah. Okay, I pasted on the upper corner. Okay, so here, very small. Now you know what I need is, what I consider is the case where, you know, the system is linear. So that the data equal h times theta plus w. But, you know, we know h is it might be a convolutional matrix, and that is a case of filtering. So it's a block of filtering because I'm considering a block of data. So this model, as we have seen, applies for equalization, applies for deconvolution, equalization are the same, applies for estimating, identifying the system, and the system can be with one filter, but it might be with two filters, see the lab we did, or, you know, any arbitrary. Now, so if I assume that W is Gaussian and theta is Gaussian, then I mean plugging there, okay, it gets the MMSE estimator, which coincides with the map, okay, because it's a simplified case of the one before. So, you know, it's a big formula. That's it. You know, I cannot tell you more to digest this formula. That's the shape of the formula. So, looking at the formula itself, I mean, let me see what I can suggest here. Now, this is the behavior. This is a CXX. Okay, but you know, CXX is obviously this way because this is a linear transformation. So, if I calculate the covariance of x, is the covariance of theta times h c theta theta h transpose. So, here, you know, what I see is CXX, which is to the minus 1, okay? So, and then, I mean, the part before and after, okay, this is C theta x, and the other is x minus mu x. Okay. So, you know, and the covariance is defined still by substituting. Now, as I said, notice that, you know, since this matrix is a positive semi-definite, it comes out that the covariance of theta given x is smaller or equal than the covariance of theta, which means I improve. Okay? So this one says, you know, I mean, I can only improve by making the MMSE estimator. Or, I mean, it goes as much as. Okay? That's what it's saying. So, you know, I mean, this is to say that the MMSE improves with respect to a priori only, or at most does not degrade the performance. Okay, so I mean, I'm not destroying anything. Okay, it goes as much as, or it goes better. Okay, so this is a strong argument in favor to use the MMSE, because I mean, in the worst case, it does nothing. Okay, so perhaps, I mean, you can also skip. So if you have a problem, perhaps what you can do, what I recommend you know, is the following. In case you have a problem, since everything depends on this C theta x, let me write to you for that. So, since everything depends on that, now, if x and theta are not correlated, okay, you better use a priori only. I don't know who I was discussing, I mean, 2 days ago. Was discussing with someone. I'm not sure he's here. So, I mean, and we're discussing, and you know, the question was, I mean, how do I know that? I mean, I can cancel the noise, okay? And then my answer is, I can cancel the noise the interfered music. Okay, I can cancel part of the interference because I mean there was the signal with or the file with music plus noise plus interference, and then I get another one which is interference. So since you know the correlation between the two is that they correlate only on the interference side, not as a music and noise. So that part which is correlated is cancelling out. Because I mean, this is what is the filtering done. This is the purpose of the filter. So in other words, I can only cancel that part that is correlated to the other signal that I'm using as a reference. If not correlated, give up. Don't do anything. Don't waste your time to compute. Now, mapping here. If these covariants, C theta x, are not correlated, so if you look at that, you try to numerically calculate the correlation between x and theta, or analytically, you know for some reason, and you try to calculate, you find that you know the two terms are not correlated. That means that this matrix is close to zero, okay, or you know it's never zero in engineering. It's close to zero. Okay, it's small, very small. Then give up. Don't do anything. Okay, because I mean you're making a lot of computation with gaining almost nothing. Okay. So now we mentioned that before. Okay. So the principle of orthogonality, and you know I introduced the principle of orthogonality. I mean making some different arguments from here. Now in many settings the linear estimator is so nice, it's so beautiful, it's so easy, it's so appealing, it's so easy, let me say, easy and computationally efficient, because I mean you have a matrix time vector multiplication, so most of the time I mean you have if you buy a digital signal processor and you go to the grocery and buy one of that, you will see that there is always a matrix time vector multiplication. Okay, if you buy one now, if you go and look at the data sheets of digital signal processors 20 years ago, you will see that there is not of a matrix time vector multiplication. Okay, so this is reflecting the evolution of the subject. So, I mean, 20 years ago I was not teaching this part. Digital signal process was not shaped in this way. So it's evolving, okay? Now, so because of that, you know, let's see how I frame it. So now when I say that I want to use a linear estimator that is constraining, so it's minimizing the mean square error, then what I do, I try to minimize the mean square error. Right? But since I constrain the estimator to be linear, then what I say is that I am deriving the linear MMSE. In other words, putting the linear, the L into the MMSE means that you are using an estimator that you know that might be optimal if everything is Gaussian. But you know, if it is not Gaussian, it's not optimal at all. Clear? Okay? So this L, okay, is a kind of self-excuse which is saying, I know that the estimator is not optimal because my processes are not Gaussian. But you know, the estimator, the linear estimator is so easy and beautiful to calculate that I make a linear one. And I accept some loss in favor of computational simplicity. Now let's make the cartoon example. So I mean, I told you that this was the case of Gaussian, but you know, if I say that the position where I am is distributed, so the a priori is distributed by two. Okay, what I'm sketching is the a priori distribution. Yeah? Now, you know, if I say that the a priori distribution is behaving this way, Now, you know, this one might be a Gaussian mixture. This one might be, you know, a bidimensional Gaussian mixture, okay? So, this means that, you know, I have a Gaussian here, a Gaussian there, with a different correlation, so they're tilted in a different way. And then this describe p theta. Now, this p theta is non-Gaussian, right? This one is non-Gaussian. Then my goal is to say, okay, I would like to use, you know, a linear model. I would like to use not a linear model, a linear estimator. So what the linear estimator does implicitly? The linear estimator does implicitly, now after we derive, you know, the linear estimator does implicitly say, this a priori is Gaussian. And this is the Gaussian that I'm considering. Okay? So the dash in here is the Gaussian a priori corresponding to the two non-Gaussian ones. Now clearly, if you say, well, if I take the mean of the a priori, I get a disposition. Okay? So, I mean, if using this model and you ask yourself, where I'm going to be, then you know I'm going to sit on the connector to the Y, which means I'm sitting in front here. Because that is the mean between being there and being there. Right? Now, this solution doesn't make any sense. Okay? So what I'm saying is that, I mean, the mean on the a priori, which is corresponding to this large Gaussian, okay, makes no sense. Now, you know, but if I combine this with the measurement, and the measurement is Gaussian, then what I get is, I don't know, I get something that perhaps is broader than before. Okay. Here was a thinner, here is broader, okay. But you know, so that is the Gaussian, that is the Gaussian a posteriori. Now, the Gaussian a posteriori starting from the Gaussian approximation of a non-Gaussian a priori. So this Gaussian a posteriori, now it's not correct, okay? But you know, all the operations that I've been doing from the dashed line to this one are linear. So, you know, that means that making a linear estimator is, in some setting, very convenient. Now, let's make an example before I go forward. Let's make an example for the telecom. Now, if I go back here. Now, the telecom students, they know very well this example. Okay, they saw the communication system, digital communication, okay, and so forth. Now, so for in this setting, I have theta that is, you know, is represented by a binary signal. Okay, so theta is the bits. So theta is 1 with probability p, and -1 with probability -1 minus p. Okay, which is binary and antipodal. Okay. Now, usually, you know, p, the probability is 1/2, it's 50%. Okay. So, what is the distribution in this case? The distribution is represented by 2 delta, -1 and +1. Right? Okay, now, let's calculate the variance here. What is the variance? Well, the variance is 1 squared multiplied by the probability 1/2 plus -1 squared, which is 1 again, multiplied by the probability 1/2. So the, you know, sigma theta, which is the variance of theta, is equal to 1. Okay. But now, you know, I can start from here and use the Gaussian approximation. So what does it mean? It means that, you know, my a priori PDF is this one, which is a Gaussian. It's a Gaussian with 0 mean and, you know, with the sigma that is equal to sigma theta, which is equal to 1. Now, the a priori is clearly non-Gaussian because I have delta plus minus delta, right? And, you know, and the approximation is for a Gaussian one. So if I tell you, you know, looking at here, I ask you, what is the value of the most likely value of theta? Then you answer to me on the a priori information is 0. You know, 0 is not even accounted as a bit, as a level, okay? So now clearly it makes no sense. That's another setting. Now, so if I am in a setting where, you know, I'm clearly non-Gaussian, but I try to use a Gaussian anyway, I use the so-called linear MMC. Now in the telecom context, the word linear disappears, okay, because it's too annoying to write linear. And then, you know, it's called the MMC. But, you know, I mean, this is under the linear assumption. So, given that, you know, let's start. So what I do, I write theta hat is equal to A0 plus A multiplied by X. Now, this model, which is the estimator, resembles the blue estimator, except that now I need to minimize the mean square error and the bias, the Bayesian bias. So now, similar to blue. So, I mean, I get, you know, so I get A and A0 by optimizing, which means minimizing the mean square error and Bayesian bias. Okay. Now, you know, for the analytics, go to the book, because I mean the result is exactly the same that we computed now. So if I make, okay, so go to the book, if I make it this way, then, you know, my linear MMC has the same formula as the MMC estimator for Gaussian setting. But in fact, we implicitly assumed it was Gaussian. And the covariance of the linear MMC is the covariance as before, which is c theta theta minus something. Okay. Now, since the linear MMC is an approximation of the MMC, so what I know is that the covariance of the linear MMC is larger than the covariance of the MMC. No, but you know, remember, these, yeah, I call it here true MMC. So these true MMC is non-linear. So what happens here is that, so in other words, it means that this one is larger or equal than that. So, you know, what's happening here is that the covariance of the linear MMC is bigger than the covariance of the MMC estimator, which is the optimal one, which is non-linear in this case. Remember the story of the bit? That was non-linear. Okay? So the price you need to pay, simplicity, which means a linear MMC, is paid by a performance loss. Okay, the performance loss is here. So now you know. Let's see if there is if this linear MMC is fulfilling some other condition. Now, the linear MMC fulfills the condition of orthogonality. What is the orthogonality? The orthogonality says the following: that that if I take theta minus a, depending on a is the estimator. So this is the error, theta minus a times x, and this is the error. So the error multiplied by the x transpose, which is the data transpose, the expectation for that, which is, you know, is computing the outer product, is this. Now, this one is the orthogonality condition. So this says that x, any value of the random variable included in the vector x, is statistically orthogonal to any entry of the error in the vector x. I'll say it again. This condition says that, you know, any entry in the vector x, which is representing the error, is orthogonal to any entry of the vector x, which is representing the input. Any entry means any element of the vector. Okay? So this I can write differently. This means that the expectation of any entry, let me say epsilon k x, is orthogonal to any entry of the vector x and call n is equal 0 for any k and n. This is the scalar representation of the same setting indicated. Now this one is called orthogonality condition. Now, what does it mean, orthogonality condition? Now, so if I rewrite, so if I represent theta equal to theta hat plus the error, so that means that theta can be decomposed into the estimate into component that is orthogonal to the estimate. So, in other words, this is saying that the estimate and the error are mutually orthogonal. Now, this is also called the Pythagorean theorem in statistics. Okay. So now, no, this is not for you, because these are slides I took for other courses. So, you know, I can calculate the Bayesian Kramer-Rao bound. Okay, it can be computed. You can compare with the Kramer-Rao bound, Bayesian Kramer-Rao bound, and then you can always get compare with that and see if you're optimal or not, if you're good or not, and so on. Let's skip it. Okay. Now, so far we have been dealing with so far we saw, that's what we have seen, you know, we have seen that otherwise the movie doesn't come out very nice. You see, does it see the board when you look at the screen? You see that one as well? I never see myself. Okay. You have a big passion, so that's good. Do they pay you? You should get money. You should say every time you see, you need to give me a click, and then you know.
Put some advertisement.
Huh?
I can put some advertisement.
Right. So what we have seen, you know, let's review. So we have seen that in a block size or in a block type of processing, I need to get my a posteriori. From the posteriori, you know, I can get the mark, I can get the MMSC estimate, okay, which is the max or the mean. Then today we've seen that if Gaussian, so if a p x theta is, is Gaussian, so it's normal. Let me put it simply this way. As normal, okay? Then in this case, the estimator is linear. We have seen in a very simple case that if x and theta, they are not Gaussian, then, okay, we got that the estimator is complex. But as a suboptimum solution, I can use the linear MMC, which means x and theta are approximately Gaussian. Okay, so if I do this way, then I get the covariance of theta linear MMC. Okay. That is larger or equal than the covariance of theta MMC, which is non-linear. Okay, that's a summarize. Further, okay, this one can always be computed. By knowing the moments. That's what we derived so far, okay? Can always be computed. Now, of course, if we are in a Gaussian setting, then what's happened is that the linear MMC coincides with the MMC. If it's Gaussian, okay? If it is on Gaussian, then we can always compute the MMC. We can compute the linear MMC, okay? So the linear. Now, so far, we are dealing with block of data. So we are not dealing with signal. Now, you can always take a block of data and then consider that this block of data represents the signal. Now, you might ask yourself, but how? What is my estimator in case the signal is representing a random stationary process? And this goes into the chapter of optimum Wiener filter. Now, the optimum Wiener filter is constrained to have a stationarity of the signals involved. So I'm dealing with the stationary random processes, and in this case, I can design the filters in such a way that they are optimal. Now, if it is if it is a stationary process, past and future they are statistically the same. Which means that the correlation, in fact, when you calculate the autocorrelation, when you calculate the autocorrelation, your index goes in front and in back. So you are correlating the signal with the front and the signal with the index on the back. Okay? If it is not stationary, you cannot do that. No, just to make a very stupid remark. Now, consider, okay? So we are now, we close the chapter, so we close the part related to finding the optimal or suboptimal MMC estimator for a block of data. Now look at a case, let's look at a case when we have a random process which is stationary and we have an infinite number of samples. And this is the optimum Wiener filter. Now, Linear filtering is the following. So what is the problem? The setting of the problem is the following. So assume that you know my xn, you know, and this xn is stationary random process. Okay. So since it's stationary, you know, it doesn't change in time. Okay. Now what I do is this. I want to use xn to estimate a certain theta. Okay. And then my estimated theta is theta hat. Now this theta hat, okay, depends on the set of coefficient A. So in other words, what's happening is this. I have xn, I'm taking a block, not a block, sorry, an infinite set of data, so let me put it this way, to estimate theta hat. Okay. Now, so I'm putting together all that by combining according to the certain filter that I indicated here, and I estimate my value. Similar to the lab, except that now, you know, you're not constraining, you're not saying that it's causal, anti-causal, and we're not constraining that it's finite. We're not saying that the length is 20 samples, 30 samples, 100 samples, okay? It's infinite number of samples. So now, how it works? So what I do is I make a convolution between my process and my filter. And you know, the filter response, which is represented by these AK or AN, is infinite. So I have an infinite filter response, infinite length filter response, that is taking a set of, you know, a set of random values, which is representative of the random process, and wants to estimate theta at the position n. Okay, so that's the problem. Now, you know, my goal is to get A. Now, this filter is my estimator. So the estimator is this filter A. Okay. Now, you know, about the process, even theta is a process. So, you know, that means that I have a set of data x, which are representing the process, that are used to estimate theta, that is another process. Okay? So you can imagine similar, you know, to have two random processes, one on the top and the other on the bottom. Okay, it's like here. So what I do, I estimate, I compare with this, and then I get the error. Okay, similarly as you did in the lab. Okay, 2 days ago. Now, so let's write the problem. Okay. Now, writing the problem, I can write the problem, then I can write the error. So what is the error? Now, writing the error is epsilon, that depends on n, and then depends on the set of coefficient a, n. The error is theta n minus a n convolved by xn. And this is the error. Now the error depends on coefficient, set of coefficient of the filter. Okay? Now this filter, you know, is the estimate of filter in our case. So what we can do the following. We can take this error and minimize the mean square error of this error. So, you know, in other words, what I can do is I can take the expectation of this epsilon compute the square and set it to the minimum with respect to the set of coefficient A. So I can essentially calculate the set of coefficient a n such that is minimized with respect to a n what? The arrow. So the arrow which is where is it? Theta and minus x and convolved with a n squared. Okay. Now, what makes a little bit tricky the problem? The problem is that what makes it complicate, if you like, is the fact that the filter that I'm looking at, which is the filter that minimizes, this is the error, okay? And this, I forgot the expectation. And so this, the filter is the one that minimizes the mean square error. Okay? So what I'm finding the filter that minimizes the mean square error. So is the minimum mean square error filter. Okay? Now this filter that minimizes the mean square error is called the Wiener filter. So the Wiener filter is the filter that minimizes the mean square error, okay, without constraining the filter itself to be minimum, maximum phase, or whatever. Now, rather than taking the expectation, computing everything and so on, a very straightforward way is to go through the polynomial, which means go to the z-transform. So rather than dealing with the signal in time, I deal with the signal in a z-transform. So if I deal with the signal in a z-transform, my error, let me write on your page. So, writing as a z-transform, then, calling theta z as a z-transform of theta n. And, x z similarly and a z similarly. So the error Ez, okay, which is a z-transform of the error, the error can be written as, so it is theta z, so z, right, first time, minus it's x z a z, okay, then I need to compute the square, which means I need to compute the complex conjugate of the coefficient, okay, and with the opposite, with the flipped direction, so it is theta 1 over z minus x star 1 over z a star 1 over z. Okay. Now, so rather than computing this way, since my error, I skipped one step. So the error Ez e star 1 over z is equal to that part. Okay, that's the error. So, what I need to do, I need to take the expectation for that, which is equal to the expectation for the other. Okay? The expectation for all the others. Then what I need to do, I need to calculate the derivative of this one with respect to the set of coefficient AZ, because this is my unknown, and set this to 0. Now, when I set these to 0, my result is the following. Then, if I calculate the error, so it is 2 times, it is the expectation of error, which is epsilon time x star 1 over 0 equals 0. That's what comes out. Because I have a square, so it's a square. The derivative of a square is 2 times the value times the derivative of the part in term minus. Okay, now if I look at what is this error about, then I can find that it's expectation of theta z minus x z times a z multiplied by x star 1 over 0 equal 0. And now, this is the error, and that is x star. So this is the expectation of the error time the input. So this one is the orthogonality condition for y sense stationary sequence, which is the condition for linear filtering, the general condition. Okay. Now let's apply in one example. It's not in the slide, so I take from here. I have no time to put it into the slide. So let's make an example for that. Where is it? Now, let's consider the Wiener filter for deconvolution or equalization. So let's apply that. Let's make the example to close the day. Okay, so let's assume that I have the filter Hn. And I have a sequence Wn. And then I have a noise. The noise is this Z. Okay? This is what I call X. So my goal is to put an estimator here, which I call An, in such a way that I get an estimate of W hat. Okay. In such a way that the error is minimized. Okay. This is my number. So now since I'm assuming that all the processes are stationary, this Y sense is stationary, they're Gaussian, perfect. Okay, so what I can do, I can use the orthogonality principle to derive the Wiener filter. So what does it say, the orthogonality principle? Now the orthogonality principle says that I need to set the orthogonality with respect to the error. Now what is the error? The error is W hat minus W hat. Okay, that's the error. Now where is it coming, W hat? Let me write it different, let me write it so that it's similar to the text. Okay, so that's W minus W hat. So Wn, okay, which is the input, is a W hat is Xn convolved by An. and AN is the filter to be established. Now, I put the orthogonality, I use the Z transform, and I put the orthogonality condition. Now, so what is the orthogonality condition? The orthogonality says that I need to have the orthogonality between the Z transform of the error time the input with the input, with the sequence input. So the error, which is W Z minus X Z time A Z orthogonal to the input, which is X star 1 over Z. These overall should be orthogonal. Now if I solve in this way, I get the linear filter. So this is the condition for linear filter. Now let's compute it. So I have that. So the expectation is not acting on A, is acting on X and W. So let's write it. So I have expectation of X, Z, X star 1 over Z multiplied by AZ, that is unknown, equal to expectation of WZ multiplied by X star 1 over Z. This is my unknown. Okay. So, my A linear is equal to, so it is expectation of WZ times X star 1 over Z divided by the expectation of X, Z, X star 1 over Z. Now, let's go deeper. What is the expectation of X, Z, X star 1 over Z? Now this is the Z transform of the autocorrelation of the Z. So, continuing writing, this is the autocorrelation Rx X Z. And the output part is the cross correlation between W and X Z. Okay? Now let's calculate the autocorrelation. Now let's write here. Because this way you can go. By the way, you have also the book. So I want to do it here because I want to tell you how to make it the first time. So now, how to compute the autocorrelation on X. So R X X Z, okay, which is Z transform of the autocorrelation sequence, is the autocorrelation of Z. So it's R Z Z Z transform plus it is R W W Z times A Z H star 1 over Z. Because I'm using that one. Okay, I'm using the fact that the autocorrelation here is the autocorrelation of the process Z plus W filtered by H. Okay? So it is W, this one is W, and filtered by H. Okay? That in Z transform, this one is X, and in Z transform, is xz, which is equal to wz times h0. Okay? So if I need to calculate xz times x star 1 over z, this is equal to wz times w star 1 over z times hz h star 1. When I apply the expectation here, the expectation goes here because h is a filter, and this is RWW. Okay, so you should get practice with this computation because this was part of the intermediate exam number 1. Okay, so I know the autocorrelation of the or the z transform of the autocorrelation in x, so I know the denominator. So I continue here. So the filter a z of the VLAN is denominator, so it is r z z plus r w w z times h z h star 1 over. Now the numerator is wz times h star 1 over z. So what is h star 1 over z? H star 1 over z, okay, you see there, so that's wz expectation of time. I have wz and xz. So what is xz? Is z lower up, so capital Z plus is W times H Z. Now this one are X Z. Now I need to calculate here. Is indicated X star 1 over Z. So that means that I need to calculate the star of this one. So I have star here, star there, star here, and I know it's 1 over z. Then I need to compute the expectation of w times z. So w is the input, z is the noise. So this expectation is 0. And then I have the expectation of w times w star, which is the autocorrelation of w times h star. So this is equal to r w w z times h star 1 over z divided by that. And this is the most general result. Now let's specialize in some setting. So I continue here, so I can access to these results, and then I specialize. Now let's specialize in this way. Let's assume that okay, let's assume that Zn is y, is stationary and y. That means that r z of z is equal to sigma squared z, okay, because it's y. That means that the autocorrelation is r z z k equal to sigma squared z multiplied by delta k. Okay. Then let's assume, to simplify, that the w, the input, and wn, which is the input to the system, is y as well. Okay. So let's see. Yeah. I don't know, it's the voice, it's the music, is the lab of the last day, okay, 2 days ago, is white. Now, in this case, you know, RWW is sigma squared W, and this means again that the autocorrelation W is white. Now, let's take that formula, which is the general one, which I just copy, the general formula, okay? So, Wiener formula, RWW times H star 1 over Z, and then I have RZ plus RWW of Z times HZ H star 1 over Z. Now, under the assumption this is equal to sigma squared W H star 1 over Z, and then it is equal to sigma squared ZZ plus sigma squared WW times HZ H star 1 over Z. This is the general way. Now I can make some comments on that. Now, comment number one. So remark. The remark number one is that you know, if AZ as a pole, A star as a pole. If AZ is a 0, A star is a 0. Okay. Now, if AZ, since you record, you know, listen to me. So if AZ has a pole and 0, okay, then you know A star has a pole and 0. So all the poles now are symmetrical, okay, reciprocal symmetrical with respect to this one. Okay. Second, you know, if AZ has a 0, you know, putting here, I have a 0 inside and 0 outside of the circle, which means that now these are poles. So I have a settle pole inside, a settle pole outside of the circle, symmetrical. Okay? So forgetting about the numerator, if HZ contains only 0, the filter contains poles that are inside and outside of the circle. So that means that if I have a pole inside, the system is causal stable. If I have a pole outside, the system is anticausal. So overall, the response is causal and anticausal, represented by poles. That means that the response, the impulse response of the filter is not causal, is not anticausal. It's causal and anticausal. It's not limited, it's infinite support, it's infinite length. So the Wiener filter is not limited in length. The limit of the filter, in principle, which means in the most general way, is either causal, anticausal. That means that it's infinite in length. So you notice here that the Wiener filter, differently from the previous one, think about the lab, you set the length, you decide that if the samples were too much of, you know, fluctuating, you cut it out. You don't estimate those samples. Here, we keep all the samples. Here, the filter length is infinite. So, remark number one. Let me make it. The remark number one says, if HZ contains zeros, then, you know, AZ contains poles that are symmetrical with respect to the radius 1. unit radius. That means that the filter is causal and anticausal and infinite length. Okay? Now you understand why we made a block processing, because in block processing we restrict the block of data, we restrict the length to be 20, 30, 40. We shape the filter to look at only where the data are more important. Here we have not these degrees of freedom. You choose the filter is infinite length. Now the telecom, they started getting smart to take these binary filter, cutting the filter, finding the way, but you know, this is a trick, okay? So you can either apply these tricks, or you know, you can use a block processing. So this is a strong argument in favor of block processing, because in block processing, you start to design the estimator to be limited in length. Here, if you cut the filter response, your filter, which is your estimator, is absolutely suboptimal, because you are trying to shape the estimator by cutting it to make you know, somewhat of the job by reducing the cost and so on. But that estimator is an unavoidable suboptimal. The second remark, I need to look at a little bit more on the filter. Now, let me copy here. So this is A dinner. Now, if you want to have a filter in frequency, so if you want to have A omega, you know, it's enough that you take A Z and you apply Z on AJ, okay? So, you know, you can always do that. Okay? So that means that the filter is sigma squared W times H star omega, and then I have a sigma squared Z plus sigma squared W times H omega squared, okay, because it's H times H star. Okay, so now let's make some assumption. Let's assume that, you know, for some reason we sketch a spectrum with respect to omega, okay, and so we make the assumption that, for instance, the filter is a low pass filter. So let's assume that what I sketched here is H omega. Now, if I draw H omega in this way, you know, what are you going to expect to be the filter? Now, if this one is a low pass filter, approximate low pass, because you are cutting out, because the filter response is keeping the low frequency and cutting out the high frequency, okay? So in jargon, it's called a low pass. So, you know, this filter, this H omega is a low pass. Now, what is doing the inverse filter? Now, the inverse filter, if this one is a low pass, the inverse filter should be high pass, okay? So that was homework number one. In homework number one, you know, you have a filter, you need to apply the inverse, whatever it is. So, you know, your inverse filter here is something ideal. It's something that, you know, it starts growing, okay? So that is approximately 1 over H omega. Okay, this is the inverse filter. Now, you know, assume that, for instance, you have noise. You know, in this problem, we have the noise as well. Let me sketch with this pinky color. And this is the power spectral density of the noise. So the noise we call sigma z. Okay? Now, if this is the noise, so we can sketch two different possibilities. The possibility number one is, okay, here, equal. Now, if the noise is very small, okay, which means if sigma squared z is much smaller than sigma squared w multiplied by absolute value of h squared, okay, then in my Wiener filter A Z, okay, becomes becomes a filter where we have sigma w. Now if this one is very big, this disappears. So I have sigma w, and this goes away, okay, and then it is h star, and it is h star. So h, the filter is 1 over h, which is exactly the filter, okay. So in other words, we say that when the power of the filtered signal is much larger than the level of noise, then what I do is the inverse filter, the optimum linear filter, is the inverse filter. Now what's happening the other way? So let's assume that this inequality goes on the other way, the other direction, which means that it's noise dominating. So what's happening if it is noise dominating? Now if it is noise dominating, that means that in this equality, this is bigger than that. So then we have sigma w divided by sigma z multiplied by h star. Now looking very carefully, since this sigma z is bigger than that, okay, so now that means that this ratio is going to 0. So essentially what's happened is that if that condition, then AZ is approximately 0. So now it means the following. If we pre-multiply now with the filter the sigma z, this behavior is also equivalent to sigma w squared multiplied by h squared, which is the power spectral density output of the system. Now the system is saying the following. Here, okay, in this region, sigma squared z is much smaller than sigma squared w times h squared. So in this region, signal dominate. When the signal dominate, the optimum filtering is the inverse filter. Okay. Now, what's happened on the other direction? So, in this area, sigma z is larger than sigma w times h squared. Then here, noise dominates. So when the noise dominates, the optimum Wiener filter is 0. So how is the optimum filter? Now, if you sketch the optimum filter, you compute by MATLAB or similar. What you get is that the optimum Wiener filter is behaving as the inverse filter as far as the signal to noise ratio is higher than 0, higher than 1, and is behaving as an attenuating filter whenever the signal to noise ratio is smaller than 1. So when you are in a region where the noise is dominating, it's better not to take the signal and amplify it. Because otherwise, if I am here and I would apply this inverse filter to the data, I amplify this noise, which is now bigger than the signal. And so that will be, something that is destroying the signal in that part of the spectrum density where the signal is weaker than the noise. So when the signal is weaker than noise, it's better to shut up. And so, you know, what is the winner saying is a gold rule. If you don't know what to say, put to 0. If you don't know what to say, shut up. Don't say. If you are at the exam, rather than saying something stupid, don't say. If you write something that makes no sense, don't write. Okay? If at the exam I ask you to write, to solve something, don't write me a poem, because if the poem is right, you get no benefit. If the poem, I'm talking about poem, which means many pages. If the poem that you're writing is wrong, you are penalized. Okay? So that's the same, if it is a noise dominated, go to 0. Don't amplify the noise, because that will destroy that part of the signal where you have a good signal. No, this new interpretation about the Wiener filtering, and by the way, the Wiener filtering is the MMSE. So now revisit your results. Listen the sound of the music and the train. You will see that in some cases the signal, the clean signal, starts to be low pass, which means dominated by the low frequency component. This is due to the fact that the train is in a high portion of the spectrum. Because the signal is weak in that portion of the spectrum, the LMS, which is implementing an MMSC filter, is saying the following. Rather than destroying completely the intelligibility of the music, I attenuate this signal in the high frequency part. Now try to revisit your lab. Try to listen to the music that you cleaned up, and try to see, because I remember some. Moving around the table, I remember in a couple of cases where I started to listen to music when the music, was low volume, the frequency content starts to reduce. You don't realize by making a spectrogram. You realize by listening. And you will see that the music was losing at the high frequency, and you got music that was with a low pass dominance and not with the high frequency content. Try to revisit that, perhaps giving this key to lecture to interpret your results. You might realize some of the results that you get, which are perfectly in line with you.